All right, this is chapter 10, at least the part in chapter 10 that we didn't preview earlier. And so I'll get into what chapter 10 is. But I want you to think about this. What was the very first thing you ever learned mathematically? If I ask students this, sometimes they think the first thing they learned mathematically is addition. Certainly wasn't multiplication. In fact, you might have been old enough when you learned multiplication to kind of remember it. I don't know. Maybe not. But the first thing you learned mathematically was counting. But there's something else, and I'm going to make this clear. This is required of everybody in kindergarten. And that is skip counting. So skip counting would be by twos, would be 2, 4, 6, 8, 10. And so the way we'll go in this class, we'll describe it by starting with a 2 and adding 2 every time. So everyone, probably in the age of 5 or 6, learned 2, 4, 6, 8, 10. Usually the next thing students learn to skip count is, can you see what I wrote there? Yep, skip counting is 5s. 5, 10, 15, 20, 25. Well, we're going to talk about skip counting. But before I get into what we're going to talk about, let's talk about what we already have talked about. So we certainly don't really talk about adding, and I mean, we use adding, multiplication, I guess counting. But in chapter 2, you had something like this. F of x equals 2x plus 3. That's not a list of numbers. It's not skip counting. But in chapter 10, that's exactly how we picture it. So what do we do in chapter 2 with 2x plus 3, f of x equals 2x plus 3? Well, I don't think we ever made a table this big, but we make tables. So you pick your x values and calculate your y values. And let's just convince everybody that this is true. If I put in a 1, I'll get a 5. If I put in a 0, I get a 3. Yeah, I just picked my x values, calculate my y values. So here's what we're going to do in chapter 10. We're going to get rid of all of this table except for this. Starting at 1, or starting at when x is 1, and we get 5, 7, 9, 11, 13. We're just going to make a list out of that. And so this list is that list, and we call it a series. So that's what we're going to talk about. Series of numbers, like we're skip counting, but the skip counting is a little more random than it was in kindergarten. It's not like you have to start with a 5 and count by 5s. Here we started with a 5 and we're adding 2 every time. Doesn't have to be addition, but just so we understand. Any pattern of numbers, any series you can think of as skip counting on steroids. All right, so as our first example, I chose to take this list right here and add 1 to every term. All right, so I'd get 6, 8, 10, 12, 14. So what could they ask us about this list? Well, there's quite a bit they could ask us about this list. 4 or 5 things. All right, but to connect this to chapter 2, they might ask us for the formula that makes this list. But they wouldn't ask us in chapter 2 notation. By the way, it is 2x plus 4 because remember I added 1 to 2x plus 3. In other words, if these are the numbers that 2x plus 3 gives me, when you have a 1, when you put in x equals 1, followed by 2, 3, 4, right? If I add 1 to everything, it would be 2x plus 4. But the first thing we have to learn is we don't use this notation in chapter 10. we use this notation, right? Instead of f of x, we say a sub n, and just instead of x, we use n as the variable. Now, we'll come back to this type of problem. I guess I can say one thing about this, and that is we call the first term in the series, it goes by two names, either a or a sub 1. A sub 1 meaning the first term. If the 1's invisible, it would just be a. So I call it a or a sub 1. This would be a sub 2 for the second term, a sub 3. You might be asked what's a or a sub 1. So, but we're getting ahead of ourselves. All right. So here's another example, a little more mathematical, a little more work. Actually, it's two examples. Kind of don't want that one in there yet. All right. We have a list of numbers, and we want to figure out the formula, the a sub n. And best way to do this, at least in 10.1. I'm still talking about 10.1. We'll get into 10.2 later, where it's a lot easier to do this. But in 10.1, your job is to identify the invisible one, or the formula that when you put in 1, you get the first term. When you put in 2, you get the second term. When you put in 3, in this case, you get 9. When you put in 4, you get 16. When you put in 5, you get 25. And sadly, for now, it's guesswork. So you just got to stare at it and try to figure out what the pattern is. And hopefully you recognize these numbers as 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. By the way, it's a very short time. This is guesswork. This becomes more of a formula later. But hopefully you can see it. The pattern here is a sub n equals n squared. So this is the formula. When you put in 1, you get 1 squared. When you put in 2, you get 2 squared. Has to do with the formula, position in the list. All right. And then what did I do? Well, same kind of thing. Going from here to here, with this example under our belt, I chose to do this one where I added 3 to every term. So instead of starting with 4, it's now 1, it's now 4. And starting with 4, it's now 7. I'm adding 3 every time. All right. So what does that do to the series or to the formula? Yeah, this time the formula is a sub n equals n squared minus 3. So n squared is this list. N squared plus 3, I think I said minus 3, okay, is this list. Takes a little time to figure those out, but I don't want to dwell on that too long because it's not really where we stay. We kind of immediately go into another notation here. All right. But connecting a list to its formula is one of the skills we want in this section. All right, the next thing at the top is sums. And I guess I didn't finish this one up. All right. So what we do with sums is sometimes instead of putting commas between the terms, I'm going to put plus signs between the terms because I want to add them up. And we use this capital Greek letter sigma to indicate that there's going to be some adding up. So because of all these additions here. So what am I doing? I'm adding, the first term is always 1. And this is 2, this is 3, 4, and this is the 5th term. So we call them the limits, k equals 1 to 5. And yeah, we usually do switch to the letter k at this point. So you remember the formula for this? That's what's going to go here. I'll point to it. Somehow it's not working. Okay. It was n cubed plus 3, formula for that list. This time it's going to be k. I said it wrong. I was staring at a 3. It was n squared plus 3, right? Not n cubed. N squared plus 3. Yeah. That's it. That's the answer. So I mean, we could add them up and get the numerical answer, but They just want the sigma k equals 1 to 5, and then the formula k squared plus 3. And that's called summation notation or sigma notation. There's a lot to unpack on this one. I don't want to go too quickly on it, but at the same time, there's not much more I can say about it. It's not already been said. You start with 1, you end at 5, you have 1 to 5, and then the formulas that we found earlier go right there. The letters should agree. If this says K, this should say K. And just historically, we use letters I, J, and K, that area of the alphabet, for sigma notation. It's occasionally all you have to do is actually add these up. And if I was just going to add these up, I wouldn't bother with the sigma notation. I'd just, add them up like, a series of numbers. But I think you do have one question about sigma notation. All right, I'm going to stop this video and start a new one on 10.2, just to make this a 10.1 video, to make it a smaller chunk. But in 10.2, the idea starts out about the same, but we have a lot more tools, a lot more structure. It's not so much guesswork. So I think that's a good thing. All right, so that's you shouldn't be seeing that right now. That's not 10 point. This isn't 10.2. This was 10.1, and we'll see 10.2 in a little while.